Well, welcome to Slope Fields Podcast 2. Well, here's that missing problem. Remember, we were looking at this one back here. And one more. And I said, I don't know where it is. I have dy dx equals x squared and no slope field. And so I drew it over here. Right, drew it over there. Well, lo and behold, the slope field was just in the wrong spot. It's 2 pages over. Okay, and let's take a look at that one. Mine's not too bad. This one's a little bit better. And something I could point out is it helps when you're drawing these slope fields. You might want to make some of the lines a little longer than others. It kind of is easier to make the slope look. It's easier to draw a steeper slope, is what I'm trying to say. Easier to draw a steeper slope for a longer line than a shorter line, right? So, and then you can make the other ones a little bit shorter, and that might help you draw these. If I'm looking at it, the 1 and the 2 don't look that much different to me, but when you look at it all together, you can see the changes in slope. When drawing a piece of, so these are some notes on the problem from 2 slides ago and on the last podcast, but it has some, we've already seen this, because I already drew this one as well. However, it did have some nice important points here, and that is be sure your slopes of 0, 1, and -1 are infinity are spot on. Infinity means that you have a vertical line. Those should be very clear. All the other slopes must be at a steepness relative to those slopes and others around it, because it's harder to kind of draw those without reference points. You know, if you're drawing a line on a coordinate plane and between 2 points, you can draw a slope of 2. But when you're trying to draw a piece of tangent line with a slope of 2, it's not as easy. And then when, I'm going to read backwards order. When drawing a piece of the tangent line at a point, draw the line long enough to see, not so long it interferes with their tangent line. So you can make them different lengths, just don't make them run into one another. Okay? So here's the exact same function. Here you can see the horizontal tangent at 0, and you can see it on mine on the 2 pages ago. It's increasing everywhere, and that's something I pointed out. Let's look at mine in comparison. Okay, so mine's not too bad. You can see it increasing. I see x cubed there. And I drew that without a ruler. On the AP test, you'll be stuck without a ruler too. But other times you can use a ruler to help you draw a straight line. We have a change in concavity at x equals 0. That's something else we can see from this. So notice here we're concave up from 0 to infinity, and we're concave down from negative infinity to 0. Negative infinity to 0. And actually, we can only really say -2 to 2 because we don't see the rest of the graph here. We're just assuming, based on our knowledge of what the function really is, which is y equals x cubed divided by 3, that's going to keep continuing to happen. All right, and so our slope fields can tell us about our function. They can tell us about concavity. They can tell us what our function might be. So, an important tool for us. And so we're going to do some more drawing, I think, but we'll definitely do more writing the equations. I see here you have a couple tools that we looked at in the last podcast. Solving the differential equation, always is a nice idea. Looking at the pictures and identifying what do you see, what could it be, also a good idea. And then plugging in the points and finding the slopes and matching, also another idea. So you have 3 tools there to help you match. So it should not be guesswork. All right. Here we were able to match everybody, even the one we couldn't solve. All right, so we're going to match the slope field with the equation for the general equation that could represent it. All right, so first thing I notice about number 1, all right, I see waves. I see waves, which means to me cosine x or sine x. I see a wave pattern. Here I see I'm increasing everywhere. I don't see any negatives. I see all positives. Slope is increasing everywhere. My it can't fit in. So I need somebody whose slope increases everywhere. All right? Somebody who has a slope that increases. So I'm not gonna solve every single one of these, although we could, couldn't we? Get a little practice on. Actually, none of these are differential equations. Oh, look at that. None of these are differential equations. This is not a dy dx to solve. Excuse me. This page we have the function. We don't have the derivative. We have the actual function. What function are we looking at? All right. So nothing to solve here. So I'm gonna I like to kind of figure out what this could be, and then look at my choices. All right. Let's look at the first one. I think everyone sees the wave pattern. Where it's this continuing wave pattern everywhere. So that means this one and this one. All right, so we think about which one is sine, which one is cosine. How do they start off? Well, cosine goes down first and then comes up. Sine goes up. I think we have the graph of sine there. All right, so I think this one here is f. I think that's its slope field. All right, here I need someone that's increasing everywhere, which means it's not a horizontal line. It's not a linear function. If I had a linear function, I'd have nothing but the same slope everywhere. So y equals x here is just going to be a lot of the very same slope. It's going to be everywhere. It's just going to be slope of 1, right? I have the same slope everywhere. That's a boring slope field. Here, this is everywhere. This is going to be a slope of 0 everywhere. So this one has a slope of 0 everywhere. This one has a slope of 1 everywhere. This one is decreasing and then increasing. So my slope is going to be negative for x less than 0 and positive for x greater than 0, right? Because it decreases and increases. This one here has slope of infinity or undefined at 0. Right? I have a slope of 0 here, so it certainly can't be that one. So if we ruled out everybody, I think you can see which one it is. But let's rule out y equals natural log of x. What's its slope? So here I have a vertical tangent line. So this one has a vertical tangent. Vertical asymptote at x equals 0. This one has the same thing. My slope is going to be undefined at x equals 0 because we have a vertical asymptote at x equals 0. So this one here is d. So f here was y equal, or 1 was y equals sine x, and 2 was d, y equals x cubed divided by 6. So you notice we took a look and saw what we looked at the slope field. What do we notice? And then we eliminated. I gave reasons for every one of these to be eliminated besides the correct one, which was D. And this, by the way, is referring to this one. I don't know, it got pushed over a bit. All right, so hopefully this one was clear as we matched up. This time we didn't have a differential equation. We had the equation, and that's it's graphed by its slopes. Right? So we have the solution instead of the differential equation. This one is the slope field from a certain differential equation is shown at right. Which of the following could be the specific solution? So again, back here, we're matching the derivatives to the equation. So here we can plug in the values and find slopes. You can't do that when you have the equation. You can't, because the equation doesn't give you the slopes, it's giving you the function. So instead, we're identifying what do we know about that function. So the same thing here, we're going to identify what do we know about this function here. We know this one is cyclic. That slope field is not cyclic. We see it's increasing everywhere. I also notice that it's getting steeper as I get closer to 0. So the slope gets steeper as we get closer to 0. As x gets closer to 0. That's what I notice. All right, so, and notice how this, as x increases, the slope gets less steep. So just noticing, what do you see in the picture? This one, let's talk about A. A, I'm going to have both positive and negative slopes. It will not be increasing everywhere. It's U-shaped, right? It decreases, it decreases, it increases. Both positive and negative slopes. So there cannot be y equals x squared. I have all positive slopes. It's getting steeper as I get close to 0. It's getting less steep as I get closer to negative infinity, as I get closer to infinity, but it's all positive. This one would be the reverse, right? So here I would be getting, slope would get steeper. Right, this is a fast moving function, right? It gets steeper and steeper as x gets larger and larger, as x increases. So it's not that one. This one, I have a less steep slope. That's true. Decreases, except x increases what I meant to write. So the slope gets less steep as x increases. That is true. And here the slope gets less steep. So which one is it? Well, for y equals e to the negative x, that's decay. Slope is negative. I have decay. So I am right, it's getting less steep, but it's getting less steep in the negative direction. Here, my slope is positive. This is an increasing everywhere function. So that means the correct answer is E. This was y equals natural log of x. And I think, can you see him? Well, that's not necessarily well drawn. I didn't necessarily stick with one set of points either, but I think you could see it. Oops. Oh, man. I'll let go. I'll redraw it. I won't try to move it. Here, let me stick with one set of points here. There we go. So you can see that was y equals natural log of x. All right. And so here we justified in each case why it's yes and why it's no. Even if you, on a multiple choice like that, even if you do it in your, just jot down some ideas or do it in your, in your head, but you want to say, okay, which one is it? Don't guess. You can figure it out. Eliminate who it's not, even if you can. All right, so the slope field for the differential equation dy dx x squared y plus y squared 4x plus 2y will have vertical segments when? This is not one that you would be able to solve. It is solvable, not solvable by you, because this is what's called a homogeneous differential equation. My x's and y's are kind of stuck together. We can be kind of creative and get them there is a way to solve for it. It's just not very easy. And it's beyond the scope of this discussion. So, wow, it's windy outside. I just saw a garbage can go by. Literally just going by in the wind. All right, so maybe there's a hurricane, maybe a tornado coming. I don't think so. So anyway, however, we can answer this question here. So when will it have vertical segments? When our denominator equals 0, right? We're undefined. This is our slope, right? Slope is undefined when the denominator equals 0. So which one of these would make the denominator equal to 0? All right, let's figure out. So if y is equal to 0, I have 0 in the numerator, but I have the 4x still in the denominator, right? Because I'd have 0 here, 0 here, 0 here, but there'd still be this 4x. So that'd be 0. I wouldn't have vertical segments, I'd have horizontal segments. So this one would be horizontal. All right, so that's eliminated. So if you can't figure out which one it is, try eliminating it, eliminating what it's not. All right, so y, let's start from, we got rid of that one. All right, so I don't have a 4x plus 2y equals 0. That would have worked out. Y equals 2x. All right, so if I plug in 2x everywhere, hopefully we can solve this one. All right, I'm going to write it over here. This picture, by the way, has nothing to do with the picture above it. It's the first time I've used this particular question, I believe. All right, so if I plug in the 2x over into here, y equals 2x, this would be 2x cubed, y squared. I don't think that's going to make our denominator equal to 0. Nope. Right? I don't see any reason that would make it 0. All right, let's try negative 2x. All right, and I'm going to focus on the denominator. That's right. So I'm going to write down here, I'd have 4x. Oh, wait. Yeah, I'm fine. Plus 2x. I'd have 8x in the denominator. I don't know why I was even bothering to plug into the numerator. That's just extra work. We don't really care what's in the numerator. So notice that's okay. But look at this one. 4x plus 2 times negative 2x. That's going to give me 0. That's the right answer. So here, even though we couldn't necessarily solve this differential equation, we could still figure out where the vertical tangents were, and it's when that denominator equals 0. And the other two aren't going to have any impact on it. We already determined that y equals 0 doesn't make any difference. All right, let's go on to 17. So the calculator drawn slope field for the differential equation is shown below. Sketch the solution curve through the point 0, 1. So I'm going to go to 0, 1. And so that's right here. All right, and I'm going to follow the curve. All right, so notice how the curve kind of goes. So I'm going to have to go like to the right and up and down, and so I'm going to have to like cover everything. So notice that I have a kind of a steep curve here. All right, so you see how that curve is going as x increases. Over here, I assume that's 0. I can't, there's nothing there, and I'm wondering if it's got lost in the x-axis. So since I don't see anything, and I have this line here, this line of zeros, I'm assuming that's 0 as well. And then we come up, oops, we don't hang around at the x-axis. So we're 0 here at 0, at x equals 0. And then for negative 1, we're going to increase, and for negative 2, and so I don't like the way that I drew this side. Let's try this one more time. So notice we have to move across the thing. You can't stay at one x or y. And I don't know where the next, see if I'm following this up, oh, I assume it's this one here. So over, got 1, 2, here, here. Well, anyway, I just stink at drawing these. I know I can like visualize where I want them to go, but here's the 0.01. But I swear I cannot make it go where I want it to go. And probably because I'm drawing a straight line through here, and repeatedly, that's making it crooked. All right, that's good enough. There we go. Almost appears like we have some kind of slant asymptote there. And then draw the curve through -3, 0. All right, so 1, 2, 3. This one's easier. It's almost a vertical line. There we go. And you see what this must be a rational function. -3 zeros right here. Draw big enough and it hits it. So on a smartboard, this is not being all that cooperative, but I think now you can kind of see your function. So you make sure it goes through the point, and you follow along, and you keep moving to the right and to the left, right? And you don't hang on the same x value. You have to increase your x values. You have to kind of follow the curve, right? Because these are functions. And that's my last one for slope fields. I have one more podcast. I'm going to try to do it a little quicker. It's just some things on exponential equations. All right, bye. And exponential growth and decay. Bye.